Hello students, in this video we shall learn isomorphism. So let us first define isomorphism. Consider two graphs G and G dash with vertex set V and edge set E, vertex set V dash and edge set E dash respectively. Suppose there exists a function f from the vertex sets of graph G to G dash, that is V to V dash, such that the function f is a one-to-one correspondence or a function is a bijection. Second, for all vertices A, B belonging to the graph, the vertices AB of graph G, edge AB is an edge of the graph G if and only if f of A, f of B is an edge of G dash. Then f is called an isomorphism between G and G dash, and we say that G and G dash are isomorphic graphs. I'll repeat. So let us consider two graphs G and G dash with vertex set and edge set V, E and V dash, E dash respectively. Suppose there exists a function f from V to V dash such that f is a one-to-one correspondence. This is very important. F is a bijection. So let me just underline that. F is a bijection, and for all the vertices A, B belonging to the graph G, AB is an edge of G if and only if f of A and f of B is an edge of G dash. Then f is called isomorphism between G and G dash, and G and G dash are isomorphic graphs. So in other words, we say that two graphs G and G dash are said to be isomorphic to each other if there exists a one-to-one correspondence between their vertices and between their edges, such that adjacency of vertices is preserved. This is very, very important. Adjacency, not just the vertices are they have the one-to-one correspondence and the edges having the one-to-one correspondence, the adjacency of vertices is preserved. This is very important. Such graphs will have same structure. They differ only with respect to the vertices and edges, how they are labeled in the graphs and in the way they are represented geometrically. So from the definition of isomorphism of graphs, it can be put in other form, that is, it follows that two graphs G and G dash are said to be isomorphic if number of vertices of G is equal to number of vertices of G dash, that is, order of G is equal to order of G dash. Next, number of edges of G is equal to number of edges of G dash, that is, size of G is equal to size of G dash. Degrees of vertices of G must be equal to degree of vertices of G dash, or we can also say that the degree sequence of G and G dash are equal. Adjacency of vertices is preserved. So these four conditions are very important. So if these four conditions are satisfied, then we say that G and G dash are isomorphic. So let us consider this example. Consider the graph G1 and G2 as shown in the figure. So we can, very simple, if I just draw this vertex BD, right, instead of like diagonal, if I just draw a vertex like a curve as shown in G2, this graph G1 is same as graph G2. Only they differ in the geometrical representation. Rest all it is same, which means that the order of A is 3. Sorry, order of the graph G1 is 4 and order of graph G2 is also 4, because there are 4 vertices present in G1 as well as in G2. Then how many edges are there? There are 6 edges in G1, 6 edges in G2. So the size of G1 is equal to size of G2. Now, if you see the degree sequence of G1 is 3, 3, 3, 3, which is equal to the degree sequence of G2. Degree sequence of G2. So you can see that there are 3 edges incident at every vertex. So the degree sequence of G2 is also 3, 3, 3, 3. Thus, the 3 conditions of isomorphism are satisfied. Now let us see the correspondence. We can say that A is corresponding to P because the degree of A and P are equal. Then B is corresponding to Q. C corresponds to R. D corresponds to S. So thus there is a one-to-one correspondence between the vertices. Now we also need to check the edge correspondence. Edge AB corresponds to edge PQ. BC corresponds to QR. CD corresponds to RS. DA corresponds to SP. And hence there is a one-to-one correspondence between the vertices and between the edges G1 and G2. And therefore adjacency matrices of G1 and G2, if we try to write the adjacency matrices of G1 and G2, we get these matrices. Let us just go through these matrices. G1 matrix G1 is, so again you label the rows and columns as vertices A, B, C, D. And here, since there is a one-to-one correspondence between A and P, B and Q, C and R, D and S, so the second adjacency matrix in the second adjacency matrix, we label the rows and columns by PQRS. Then the A is adjacent to the vertex B, D and C. Hence 1, 1, 1, AB is 1, AC is 1, AD is 1, AA, no loop is there, so 0. B is adjacent to A, C, D. So BA is 1, BC is 1, BD is 1, BB, no loop, so 0. Similarly, you can write the 2 rows. And if you see the graph G2, the adjacency matrix is the same as adjacency matrix of the first graph G1. And from these two we can say that G1 and G2 are isomorphic. Okay. Hope it is clear. Let us go to the next example. Example 2. Consider the graphs G1 and G2. Let us check for isomorphism. So there are 4 vertices in both the graphs G1 and G2. So order of G1 is equal to 4, order of G2 is also 4. How many edges are there? 3 edges are there in both the graphs. So size of G1 is equal to size of G2. What is the degree sequence of the graphs? Degree sequence, degree of this vertex is 1. Degree of the second vertex is 2. Then the third vertex is 2. Then the fourth vertex is 1. Whereas in G2, the degree sequence of G2 is 1. How many edges are incident to this vertex? With this vertex, 3. So 3, degree of this vertex is 3. Degree of this vertex is 1. And here it is 1. So 1, 3, 1, 1. So it's clear that the degree sequences of G1 and G2 are different, and hence G1 is not isomorphic to G2. So we shall see the problems in the next video. Thank you.